So today I'm going to be teaching you guys about spirals, and I'm going to be talking a lot about the different types of spirals, but I'm also going to be teaching you guys about the golden ratio and just how spirals are used in our everyday lives. I'm sure you guys all have a general knowledge about what a spiral is, but it is a curve that rotates around a central point, getting closer or further away from that central point as it goes on. That's the mathematical definition. But not only can it be used in math, but it can also be used in art, and it can be found in different types of nature, mostly in a lot of seashells, like the conch shells and stuff. So spirals can be made in many different ways, and there are a lot of different types of spirals that exist. So the spirals that I'm going to be covering today are the clothoid spiral, the line segment spiral, the golden spiral, the Archimedean spiral, and the equiangular spiral. So I'm going to also be talking a little bit about the golden ratio and how it's just used in our everyday lives, not just in spiral. I want to start off with the golden ratio. The number of the golden ratio you don't have to memorize, but it is 1.618033988875. Yeah, so it really doesn't have a pattern, which makes it an irrational number. And it shows up in a lot of places, but it is a bit hard to explain, so I'm going to use a paper model to explain it to you guys to make it a little bit easier to understand. So sorry my camera's a bit shaky, but you're just gonna have to bear with it, but also pretend that this has not been cut yet. It just makes everything a little bit faster. So say I have a whole sheet of paper and I cut it in half. The first half I'm going to set aside, but then the second half I am going to cut in half again. Now we have two equal halves, like this. And when we look at it this way, I have proportional sheets of paper. Now I'm going to cut this half in half again. This half is proportional to this half, and this half is proportional to this half. So I'm going to cut it in half again. I'm going to scoot that over. This half is proportional to this half. This half is proportional to this half. And this half is proportional to this half. This is kind of how the golden ratio works, but I will further explain it in a minute. So that pattern of the half and half make the whole, that whole pattern is not the only pattern that's used in the golden ratio. There's also something called the Fibonacci sequence. The Fibonacci sequence is a sequence of numbers that involves that pattern. Basically the rules, it's not really a rule, but okay. So it's 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And so on. That's the Fibonacci sequence. The 2 is found by adding the two numbers before it, so that's 1 and 1. And like 3 is found by adding the numbers before it, so it's 1 and 2. And then 5 is 2 and 3, and so on. The golden spiral is made of a combination of the paper model and the Fibonacci sequence. I will show you what I mean in a second. So I have the piece of paper back again, but this time it's not cut up, but it has been split in half. I just drew it, and it has some numbers on it. These are the numbers of the Fibonacci sequence. So I'll explain it to you. Basically, the smallest halves, we have 1 and 1. 1 and 1 equal 2. If you take 1 and 2, that equals 3. 2 and 3 equal 5. 5 and 3 equal 8. 8 and 5 equals 13, and so on. And then if you connect certain parts of these boxes, it will make the golden spiral. Now that we've covered the Fibonacci sequence, the golden ratio, and the golden spiral, let's move on to some other spirals like the line segment spiral. The line segment spiral is a spiral made up of line segments that meet in right angles. Their side lengths are 1, 1, 2, 2, 3, 3, 4, 4, and so on. It's just a pattern of the next number twice. This spiral is also sometimes called the Ulam spiral. To make the spiral, it's pretty self-explanatory. You just connect the lines in right angles, and you just keep going around in a spiral formation. I will show you what that looks like in just a second. So this is the line segment spiral. It is pretty easy to draw. Basically, I took 1 centimeter and then another centimeter. So it's 1, 1, 2 centimeters, 2 centimeters, and 3 centimeters, 3, 4, 4, 5, 5, and then 6 and 6. The line segment spiral is not found in nature, but it's found in a lot of different types of art. So the next spiral I want to talk to you about is the Archimedean spiral. The Archimedean spiral was first studied by a man named Conon. I'm not quite sure if that's exactly how you say it, but it's spelled C-O-N-O-N. Later on, after Conon, it was studied by Archimedean around 225 BC. This spiral is found in nature. It is most commonly recognized as a snail shell. Now that I've taught you guys about the Archimedean spiral, I also want to teach you about the equiangular spiral. The equiangular spiral is also referred to as the logarithmic spiral. Just in case I say one, you'll know which one. You'll know that they're the same. The equiangular spiral was discovered and first researched by René Descartes in 1638, and someone else named Evangelista Torricelli helped find the length of the curve, but they didn't work together at all. And this spiral also uses the golden ratio. An example of the equiangular spiral is a hurricane, and it's sometimes found in seashells, and it can be found in art also. The last spiral I want to teach you guys about is called the clothoid spiral. The clothoid spiral is very well known as the Euler's spiral because it was researched by Leonhard Euler in 1744. The clothoid spiral pretty much looks like two spirals but connected at the ends of the spirals. Dog! So when the two spirals meet to make the clothoid spiral, it makes a perfect transition curve for things like railroads and roller coasters, so that's where they're most commonly found. So this is what the clothoid spiral looks like. It was a little bit too hard for me to draw, so I just decided I would show you. So anyway, that is the end of my video. I hope you guys learned something from it, but if you have any questions, you can email me or you can ask me in person, or you could ask Mr. Militello. So yeah.